Hi, this is John Whitaker again for the Mathematical Analysis class, and our first lecture's video got cut off short, so this is still part of lecture 1, and we'll conclude it with this video. We were talking about proving techniques, and the next proving technique that we'd like to look at is that of induction. So this is the sixth proving technique, and what induction is, it is a proving technique for statements about the set of natural numbers and it involves, so you're trying to prove a statement about each natural number. So it involves two parts. One, showing the statement is true. For n equal to 1. And 2, assuming the statement is true for n equal to some arbitrarily fixed natural number k, we must show the statement is true for the next natural number, that is k plus 1. So the way that I look at this in terms of proof by induction is we're trying to show some statement is true for each natural number. And we can't show that it's true for n equal to 1, then n equal to 2, then n equal to 3, then n equal to 4, and so forth forever, because the set of natural numbers goes on, it's infinite, and we can't get to every natural number that way individually. But what we do have is this technique of induction. What it says is if you want to prove something is true for the set of natural numbers, for each natural number, you have to show it's true for n equal to 1, and then if you assume that it's true for a fixed, arbitrary natural number, we're calling that k, then from that assumption, if you can show that it's true for the next natural number, then essentially you've shown the statement is true for every natural number. For if you know it's true for 1, and knowing it's true for 1 makes it true for 2, and knowing it's true for 2 makes it true for 3, you progress to say that you have the statement true for every natural number. Let us do an example. Okay, so as an example, someone might be asked to prove that the sum as I runs from 1 to n of I equals to n times n plus 1 all over 2. And I'll go ahead and get started with this proof. It will be by induction. So I'll tell the readers it's by induction. And the first thing we'll do is for n equal to 1, okay, I want to show that this equation is true. So I'll look at both sides of the equation. And so the left-hand side becomes the sum as I runs from 1 to 1 of I. And this sigma notation means add up what follows. What follows is a formula based on I. Well, I runs from 1 to 1, so I is just 1. And so we just get the number 1. There's only one number to add, it's 1. Now, n over n plus 1 over 2, when n is equal to 1, is equal to 1 times 1 plus 1 over 2. And that's equal to 2 over 2, which equals to 1. So you see the left-hand side of this equation is 1 when n is equal to 1, and the right-hand side of this equation is 1 when n equals to 1. So the statement is true when n is equal to 1 for the first natural number. Okay, we now want to show the second part. So assume the statement is true for n equal to k. That is, assume our formula is that the sum as I runs from 1 to k of I equals to k times k plus 1 over 2. We want to show the statement is true for n equal to k plus 1. That is, we want to show that the sum as I runs from 1 to k plus 1 of I is equal to, what I'm doing is in our statement replacing the n by k plus 1. So it would be k plus 1, and then it would be k plus 1 plus 1, so I'll just write that down as k plus 2 all over 2. That's what we want to show. Okay, so let us look at that summation as I runs from 1 to k plus 1 of I. And if I expand that sum, when I is equal to 1, I get 1. When I is equal to 2, I'm adding 2. When I is equal to 3, I'm adding 3. Plus, we keep going all the way up to k. Now, if I add a little bit more details to this expansion, that's equal to 1 plus 2 plus 3 plus, and the number right, it wasn't k, it was k plus 1. That's our last term in our sum. The number right before the k plus 1 term is k, and then we have that last term, k plus 1. And the benefit of writing it out like this is that I see that I'm adding up the first k numbers, and that's the sum as I run from 1 to k of I plus this k plus 1. And I'm assuming that our formula holds for when n is equal to k. That means it applies to here to give me the formula that this summation as I runs from 1 to k of I is equal to k times k plus 1 all over 2 plus k plus 1. And I'm adding two fractions here. And to add two fractions, what we should do is get a common denominator. This is just algebra. So the common denominator is 2, so it's k times k plus 1 over 2 plus, this will be 2 times k plus 1 all over 2. And then I can pull out k plus 1. Everything can be written down as 2. What I'll be left with is k plus 2. And all that's over 2, and that's exactly what we wanted to show. So that is that proof. We did it by induction. The last thing I want to do in terms of proving techniques is write down a statement that we'll often see in this class that we would like to prove. And I won't do an example of that, I'll just tell you how to prove it. And that is, so for 7, the statement P if and only if, and we'll abbreviate that with IFF, Q is proven by showing two things. Now prove two things. One, if P, then Q, and 2, if Q, then P. So P if and only if Q is really two if-then statements. It means if P happened, Q happened, and if Q happened, P happened. That means P and Q are equivalent in some sense. Okay. The next thing that I want to do is to go over some background material about set theory. And so sets are something that we'll be discussing in this class a great deal. And so it's good to have some background material for it. Okay. So first of all, what is a set? I'm going to start off with that definition. So we're talking about set theory. So as a definition, a set, I'm going to put this definition in quotes, is a well-defined collection of objects. The key phrase in this definition is well-defined. And by well-defined, what we mean is that if we're given an option, it's clear, given an object, it's clear whether the object is in the set or not. So as an example, let's take a look at the collection of all old people. So this collection is not a set. And the reason it's not a set is old is not well defined. So to a 6-year-old, I might be considered an old person and thus is in this set. But to my parents, I'm not an old person, so I'm not in this set. So again, old is not well defined. Another example might be the collection of all living people born before January 1st, 1950. Let's say Eastern Standard Time. And this is a set. For we can tell, given an object, whether that object is part of this collection or not. For instance, this piece of chalk right here is not in this set because it's not a living person. Whereas my mom is in this set. Okay. The next thing I want to do is make a definition of an element. So, given a set, we'll give it a name, A, X is an element of A denoted by X is in A, okay. So that's element of A right there, that's simple. If X is an object in A. So now it's just a fancy word for an object in the set. Let's look at an example. So if I take A equal to the set of 1, 2, 3, 4, 5, 7, then 4 is definitely an element of A. But 6 is not an element of A. So this symbol right here means not an element. It's the element symbol with a line slashed through it. Okay. The next thing I want to talk about is representations of sets. And so, in terms of representations of sets, we could use words, which we just saw, having the example of the collection of all people born before January 1st, 1950, as words describing the set. 2, we could have a listing of elements. We saw that as well. As an example, the A that I had just a second ago, including the numbers 1, 2, 3, 4, 5, 7. What we're doing here representing A is actually listing out the objects in A, the elements in A. And a third way we'll study is called set builder. And for set builder, what this does is it uses a defining characteristic for the elements of the set. Okay, let's look at an example of that. And so, we look at a set F, so this is an example. And F is defined by, it's the collection of objects, which I'm going to denote by X. I'm going to put this bar. This bar means such that. Okay. Also, colons can be used to represent set builder notation. And here's the defining characteristic. X is an element of the natural numbers. X is a natural number with 3 less than or equal to X less than 8.3. So that's my set F. I'm denoting it through set builder notation. Another way of listing it is by giving the elements. So what does F contain? It contains the numbers 3, 4, 5, 6, 7, and 8. So these sets are the same. Okay? There's different ways of representing them. Set builder or listing. Okay. The last thing I want to do is I want to end by looking at some specific important sets. Things that we'll look at. One is the natural numbers. So the set of natural numbers are often represented by N. Our textbook represents them by J. And what that's equal to is the set of numbers 1, 2, 3, 4, and forever in this way. Another collection of numbers that are important to us, although not vital, is the whole numbers. And so they're represented by script W, and that's equal to 0, 1, 2, forever. So it's the natural numbers plus 0. A third set of interest for us is the set of integers. And they're represented by script Z. Okay. And we've got a bunch of numbers before the ones I'm going to list, but I'll start with -2, -1, 0, 1, 2, 3, and so forth. It goes on forever in this pattern. Okay? And so this is plus or minus the whole numbers. And the last one we're going to look at for is the set of rational numbers. And the set of rational numbers are going to be represented by script Q. And what they are given by is their collection of objects that are A's over B's. So they're fractions, such that A and B are elements of the integers with one characteristic. B has to be different than 0. So those are rational numbers. And ladies and gentlemen, that's where I want to end lecture 1. Thank you very much.